Thanks, Olga, for the introduction, and thank you, Danielle. It's really a treat to be here, and you're still mesmerized by Carl's drawings, and I'm going to shift gears to a more historical project. So I'll get started. So, as the anecdote goes, somewhere between 1967 and 1974, beat poet Allen Ginsberg performed a musicalized version of William Blake's 1794 poem, The Sick Rose, in front of a large crowd at the University of California, Berkeley campus Central Plaza. The spiritual take on Blake's pastoral elegy resonated with the late 60s Berkeley climate of protest against technocracy and the alienating forces of modernity. Not with dissimilar connotations, the poem also figured as the lyrical analog for a Berkeley-born architectural treatise that, as its authors claimed, promoted, quote, an entirely new attitude to architecture and planning, end quote. A Pattern Language, as the treatise was called, was published in 1977 after more than a decade of development and testing in the Center for Environmental Structure, a nonprofit corporation co-founded in '67 by Austrian-born architect, mathematician, and UC Berkeley faculty member Christopher Alexander, along with fresh out of college architects Sarah Ishikawa and Mari Silverstein. A Pattern Language featured 253 patterns, instructions for designing parts of the environment, with each pattern including rules for combining it with other patterns. Although the definition, description, and combination of patterns were markedly characterized by formal rigor, the book was addressed to lay audiences and did not require any knowledge of mathematics. Featured under an introductory section titled The Poetry of the Language, the Sick Rose poem provided not only an exemplar of a pattern language's professed poetic potential, but also a symbol of its social vision. Alexander and his collaborators aspired to reconstruct society by operating on what they considered its mirror structure, the built environment. Permeated by, quote, a neo-romantic community anarchy structuralist vision for a human city, end quote, as Silverstein would describe it, the book sought to restore within urban environments a kind of serenity reminiscent of the one that Blake portrayed in his Songs of Innocence and whose loss he lamented in his Songs of Experience. This was not the first time that Alexander was engaging the theme of innocence. Some 13 years before A Pattern Language, Alexander had polemically announced the loss of another kind of innocence, one founded on the idea, and I'm quoting, that design must be a purely intuitive process, hopeless to try to understand sensibly, end quote. His diagnosis of the architect's loss of intellectual innocence and his proposal for a new theory of design that accepted this loss had brought Alexander to the epicenter of 1960s design debates. With the 1964 book publication of his Harvard doctoral dissertation that competed with A Pattern Language in terms of influence, circulation, and recognition for its author, Alexander had challenged the conventions of interwar modern architectural theory and preached a new kind of mathematically based rationality in design. According to Berkeley architect and urbanist Roger Montgomery, the Notes on the Synthesis of Form, as the book was titled, was the first manifesto of a worldwide movement to, quote, modernize design methods and bring scientific rigor into the designer's ancient craft. Along with a rationalizing mandate, the Notes popularized new mathematical concepts in architectural parlance, among which is the protagonist of the story that I'll be telling today, the graph. A mathematical object consisting of points that represent entities and lines that represent relationships among the entities, the graph is the subject of a field of mathematics called graph theory. In Notes, Alexander used graph theory to propose a method for grouping different requirements that a physical geometric form should satisfy into a hierarchy, a tree, which consisted of simpler groups of requirements. This would be addressed individually by the designer through schematic drawings, which Alexander called diagrams, and then recomposed in an order indicated by the tree to produce a description of physical form. This method aimed at establishing congruence between the structure of a problem and the structure of geometric physical form. At a first glance, A Pattern Language appears to stand far apart from Notes in terms of rhetoric, style, readership, and goals. Where one speaks of rationality, the other speaks of beauty and feeling. Where one parades eclectic mathematical vernacular, the other deploys a colloquial, informal language. and where one speaks to academic and professional audiences, the other seeks to appeal to lay people. Yet behind this apparent shift in rhetoric lies a technical continuum. Both notes and a pattern language run on graphs. My talk today traces manifestations of graphs in Alexander's work from the time that he enrolled as a PhD student at Harvard University in the late 50s to the publication of a pattern language in the late 70s. We will see species of graphs competing, expanding, and replacing each other. At times, the symbolic significance of these graph varieties outperformed their operational function. In other words, Alexander used the general structural characteristics of these varieties, for example, if the graph is hierarchical or not, how connected its points are, etc., to signpost both conceptual and ideological changes in his work. I talk about how different graph varieties came in Alexander's radar, the assumptions that made the one or the other kind of graph appear congruent with his theoretical statements, or the ways in which the graph's mathematical properties actually contradicted his theoretical intentions. For example, his later claims to freedom, openness, fluidity, and multidimensionality. So upon joining Harvard for doctoral studies in 1958, Alexander came in contact with émigré modernist architect Sergei Chermayev, who would become his advisor, collaborator, and co-author. Chermayev was a vocal advocate of the idea that architects should not make shapes, but should solve problems, that physical form needed to respond to social and environmental requirements. For him, modern architecture as a style stood far apart from modern architecture as an intellectual project and an ethos, one pertaining to the mandate of rational architecture, buildings designed in a reasoned manner with material economy or functional purposes in mind. In a letter that he wrote to Chermayev in the mid-60s, Alexander described his part in their relationship as one of restating more clearly Chermayev's thoughts on modern architecture by virtue of his mathematical training. This restating was significant. Alexander interpreted Chermayev's predilection for rational architecture through the lens of a specific goal-oriented, rule-based genre of rationality that was characteristic of post-war intellectual life. If Chermayev's call for a truly modern architecture free of stylistic preferences set the agenda for Alexander's work, Alexander imported the specific intellectual operations to fulfill this agenda from another adjacent modernism, one that was underway in mathematics and which he had been exposed through his mathematical training in the mid-50s. Mathematical modernism, with influential campaigners such as the secret mathematical collective Bourbaki, promoted structural abstraction as a unique intellectual operation that allowed the human spirit to break from the constraints of the empirical world and see the orders that are hidden behind it. This view came along with a boost to modern mathematical varieties that represented structures and relations. Graphs, for instance, were seen as breaking away from the empirically tainted realm of numbers, arithmetic, or shapes, geometry, and speak about structure. The cultural meanings of structural abstraction are important to keep in mind when we talk about Alexander's use of graphs. In Alexander, the graph carried both operational and symbolic meanings. It was both an instrument for achieving certain goals and a device for practicing structural abstraction in architecture with all its epistemological and cultural implications. This is Alexander's first PhD progress report, as found in the archives of Chermayev. It begins with a list of people that Alexander contacted upon joining Harvard, among which MIT-trained mathematical psychologist Duncan Robert Luce. Luce had been deploying graph theory in the 50s, the topic was not even that well known at that time, to model social groups, negotiation, and decision-making. Alexander contacted Luce to discuss the possibility of modeling the design process as a cooperative game between architects and society, in which compromises would be made among requirements placed from either side. Graph theoretic ideas that Luce worked on, such as decomposition, would ultimately become central in Alexander's mathematical repertoire. The theory of the node started being formulated during Alexander's research appointment in the MIT-Harvard Joint Center for Urban Studies, which he joined upon its foundation in '59. There he helped Chermayev to mathematically articulate a research project called the Urban House, which aimed at defining a and I'm quoting again, a vocabulary capable of describing the infinite variety of elements, situations, activities, or events that make up the complex organism house. This was a project initiated in Chermayev's Harvard seminars in the early 50s and then revisited throughout the decade. Alexander brought to this project the concept of failure as kind of the operative new term. Failure denoted a kind of physical event that prevented a human need from being satisfied. For example, sleep being prevented by bioclimatic discomfort. Because of their construal as physical events, failures not only established relationships between programmatic requirements and aspects of physical form, but also established interactions between these different requirements. Sometimes failures shared data, other times they were corrected by the same geometric sort of operations, and other times the correction of one failure aggravated the other. Similar relations of overlap, reinforcement, or conflict were then established among the corresponding design requirements. Alexander claimed that the interactions among failures could reveal the structure of design requirements, and crucially so in a non-arbitrary manner, as we see here in the underlined passage. The idea of a design problem, a set of requirements, as being underlined by a non-arbitrary structure, which could be revealed by analyzing the relationships among these requirements, also famously appeared in the seminal 1962 book Community and Privacy by Alexander and Chermayev. This structure ultimately fulfilled the deliverable of the Urban House Joint Center project, which was what Alexander and Chermayev called a working program for design. Program for Alexander was between architectural reality and mathematical abstraction. It denoted both a structure that represented a logical organization of design requirements and a process which indicated in which order the requirements should be addressed by the designer in order to produce a form whose physical organization would actually be isomorphic, mapped one-to-one to the design requirements' logical organization. So as Alexander first publicly announced in 1961, the mathematical device that would allow designers to picture this abstract structure and enact this process was the linear graph. The graph first appears in Alexander's work in a proposal for the American Building Research Institute in 1961. In this proposal, Alexander used the graph to represent highly complex relationships between requirements. He then used the decomposition method to order the graph into a neatly organized tree that depicted visually the hierarchical structure of the design problem, the order by which different requirements should be addressed. Alexander wrote, "If we do a complete analysis of a problem's graph, we get something that looks like figure 4, a nested system of systems within systems. We can make another picture of the same structure, which brings out its hierarchical form more obviously, and it looks like a tree. This tree really prescribes the process of design. You start at the bottom, solving the simplest systems of requirements, and work your way to the top." Alexander developed an automatic method for ordering graphs into trees in Hierarchical Decomposition System 2, or HIDEX 2, during a consultancy at the MIT Civil Engineering Systems Laboratory in collaboration with Marvin Mannheim. This is a tree output of HIDEX. In developing the nodes theory, Alexander, yeah, it says 7 here. I might run over a bit, so thank you. In developing the nodes theory, Alexander persistently underlined that in his method, the design, the synthesis of form, came from the designer and not from the kind of automatic method. The tree that resulted from functional analysis of requirements was only a guide for composing physical form. The hierarchical structure of the tree implied a combinatorial view of synthesis, putting together independent diagrams in a building blocks fashion, like the pictures on the bottom. Early applications of HIDEX show ambivalence towards this combinatorial view. For example, in an application for locating a highway, which is shown at the top, Alexander and Mannheim superimposed diagrams and sketched over them instead of combining them as separate entities. And they were loading in their text the synthesizing powers of the eye that go beyond combination. Ambivalence towards the hierarchical tree also appeared in the analysis stage. HIDEX 2 exhibited what Alexander called irritating anomalies that resulted from the constraint of decomposing a graph into independent subgraphs. HIDEX 3, the computer program's new version, strove to correct these problems by redefining subgraphs as overlapping as opposed to independent. Along with this corrective, a new structural mathematical concept entered Alexander's repertoire, the semi-lattice. The semi-lattice had the architecture theoretical implications that Alexander discussed in his bold, self-corrective article, "A City is Not a Tree." The semi-lattice came to symbolize a new non-hierarchical image of environmental complexity and a new phase in Alexander's theoretical expeditions. Upon assuming a professorship in Berkeley, Alexander put forward a colossal undertaking to develop conceptual components for the entire modern city. Researchers would collect requirements for different physical parts of the environment, analyze their interactions, and develop diagrams, similar to the nodes theory. Noteworthy in Alexander's research proposal, which we see here in draft form, is his derision of the unstructured nature of drawings, which he finds to be not an adequate representational device for designers. He calls them doodles at the edge of the drawing boards. The first project of this ambitious research program was the conceptual design for rapid transit stations in San Francisco. From this project grew the theoretical formulation of what Alexander called a relation. This was an interaction of physical geometric form with a behavioral, social, or environmental context. Alexander conceptualized relations as interacting and forming the so-called relational complexes. During a visiting appointment in the UK Ministry of Public Building and Works from 65 to 66, Alexander fleshed out these ideas in what came to be known as a relational theory. In it, he defined relations as geometric arrangements that prohibited conflicts between people's tendencies, which is Alexander's definition for what people naturally tended to do when they were given a chance. These relations became the atoms of what Alexander called environmental structure. Upon his return to the US in 67, Alexander co-founded, along with Ishikawa and Silverstein, a Center for the Study of Environmental Structure. The goal of the center was to document relations, which they renamed patterns, and to study their structure in order to produce the so-called pattern languages. The first years of the center were dedicated to developing pattern languages for specific projects through small grants and commissions, such as the development of a pattern language for multi-service centers in Hunts Point, South Bronx in the winter of '67. From this applied work emerged a new structural representation of patterns, which center members called the cascade. The cascade was a network of patterns arranged in scalar order, from large ones to smaller ones. It showed a nonlinear way of navigating the pattern language, which was basically, we see here part of the, I forget the exact number of patterns that were proposed for the multi-service center. And here we see kind of a deployment of the pattern language through partial sketches that were then composed to produce kind of the multi-service center design. In '68, a generous grant from the National Institute of Mental Health allowed the center to address more basic mathematical questions about the structure of the language and what they called its generativity. Generativity was about the language being able to produce physical form by relying only on patterns and their rules, and not on any external resources that designers brought to bear. Alexander conceptualized generativity as a kit of parts, finding the right patterns and their rules of combination. In this context, the participatory agendas that colored the Center for Environmental Structures' work in the turn of the '70s surfaced not as ideological or philosophical commitments, but as extreme testing cases for the pattern language's generativity. If a non-expert could use the language, then it meant that the language was kind of autonomously generative. A pattern language was the culmination of the center's work from '67 to '74. The book laid claims to participation, fluidity, and multidimensionality. Alexander described the pattern language as generalizing the one-dimensionality of words to 3 dimensions and as bearing poetic potential. Architectural elements are indeed 3-dimensional in a geometric sense. However, from a mathematical standpoint, Alexander's work did not escape 0-dimensionality. Patterns were points, symbols with no dimension. They operated as atomic units in a network which could be nested, combined, but seldom fused or restructured. Alexander turned away from the nodes, discrete logics, and strove for holism and generativity. However, a pattern language continued being vexed by the discreteness that characterized its graph-theoretic foundation. And I'm closing just with a remark, 1 minute. A pattern language ultimately suggests a clear hierarchy between the intuitive and the rational, the concrete and the abstract. Alexander viewed the richness of the empirical world as being undergirded and generated by abstract structural orders. This proposition presents striking analogies with the very condition of the computational images generation. Under the visually tantalizing universe of digital imagery lie structural mathematical abstractions, in fact often graphs, which delimit the extent of possible appearances within a creative generative process. By following the graph in Alexander's work, I have told a story in which the structuring of choice within a creative process and the structuring of physical geometric form, of shape, was not so much determined by the pragmatics of computer research, but was a deliberate move with stakes that had to do with the very status of architecture as a modern discipline. The turn from the points and lines of geometric shape to the points and lines of the graph was in fact a move away from visual intuition and towards structural abstraction as the foundation for a truly modern architecture. Yet the choice of the graph as the device for practicing structural abstraction complicates this move. The graph was itself an object that engaged the eye. It pictured, as we heard Alexander say. Alexander saw in the graph the possibility of a new kind of vision purified from the subjectivities of perception and underpinned by rational structures. A vision modeled after the graph itself, whose abstract mathematical structure underpins and delimits its geometric appearance. So I close with a provocation and invitation. The techniques on the background of our computer screens whisper stories of an anxious architectural modernism with its profound ambivalence towards shapes, seeing, and its corollaries of ambiguity and contingency. All we need to do sometimes is listen.